It's my pleasure to introduce Ricky Young, the Chief Operating Officer at qBraid. And qBraid aims to create the best quantum computing platform, comprehensive, where everyone can access all quantum computers in the end. We will have an exciting workshop today where Ricky will teach us how to optimize quantum circuits. Please, and qBraid, which I should really mention, has been a great platform partner since the start of WOMANIUM Quantum. Thank you very much for that and for your own support in that as well, Ricky. And we really look forward to your bootcamp today.
Yeah, thank you for the kind introduction, Marlu. First and foremost, it's been huge just to get started on quantum computing on qBraid for people last year at the hackathon through WOMANIUM. And this year, I think we've powered up even more. And I'm super excited to show some of the features that we have as well. So without further ado, if you haven't created a qBraid account, please do so and take your time. There will be some of our servers will have to spool up, but first let's make a qBraid account. You should see this page and you'll be able to follow along in the demo. I will mention that the demo is half live, and then the other one, which is the reinforcement learning part, is a very long training. It takes a very long time to train. So I'm just going to just gloss through the entire process that was done. And most particularly, we'll be talking about the environment and agent kind of notion that's been used to optimize the quantum circuit. All right. So do I check Discord to see if people have made an account or?
Yeah, most people should be on qBraid, especially
Okay.
after the neutral atom quantum computing bootcamp. And we shared the link too. Thanks a lot.
Yep, so that would be great. So once you have your account going, for this one, we don't have to use a blockade image. In fact, you can use whatever resources you have available. So you can have everything up to GPUs as well as the QA blockade image and Intel. For myself, I have this 2 virtual CPU, and I'm going to launch my lab. So once you have signed in, just launch your lab, and it will start your server. It might take a little while for your server to start if a lot of people are logging in. So please be patient. And once you have started your server, you should be redirected to lab. Once again, please be patient. It does take a while if a lot of people are logging in. And once you have done so, you should be able to see your account as well. All right. So I already had mine going, so I'm going to just kind of get started from here. And while everyone is kind of getting started, and I will do a quick overview of some of the features that we have, as well as our new environments just set up yesterday. Shout out to hackathons because we do a lot of them. And I'm wearing my IQ Hack sweatshirt. So I did a little hackathon of my own as well with the WOMANIUM environment today that we are going to use. These environments are essentially Python environments similar to Conda or PyM that you use, and they are all managed from our side for you to quickly get started on the base for Circuit Open Fermion, PyQuil, IBM, PennyLane, and so much more. So you can actually create your own new environments now. So if you're interested, you can create your own environment, and then you can upload the icon and actually share it with others. So that's one way of getting started quickly. And you can even share a notebook as well. So then if you ever have experienced the issue of sharing a notebook and then the person has a Windows or has an M1 Mac and then they can't suddenly install packages, you never have to face that on qBraid for quantum computing. So with that said, I want you to click the WOMANIUM Quantum 2023 environment. So for example, this one's the Pulsar one. I already have mine installed. So the WOMANIUM 2023 environment. So let me show you. It should say something like this. And just clicking install will allow you to install that package. And once it's installed, please activate it. it does take some time. It is very large. So some of the things that are in it are, of course, Qiskit. We will be using Qiskit today, as well as PyTorch and a package called Gymnasium by OpenAI.
And there is a question, Ricky.
Yes.
Will this environment also be available after the WOMANIUM quantum program has ended?
Yes, so that's a great question. So this has the tag free. So you can actually search for free environments, which I guess I have installed all of them. But all of those that are free are available to you to install whenever you like. So Matik, for example, which is the noise mitigation package, is available for free, and I think Qiskit as well. What we do offer is now, if you code frequently in quantum on a quantum software framework, you know that Qiskit has just recently done an upgrade, and maybe your notebook that you had 6 months ago no longer works on the latest version. So now we have versioned Qiskit environments. So every time you go in, you are guaranteed that your notebook works, and you just, if you are interested in maybe updating your code, you can rest assured that you can always maybe make a copy of your notebook and then work off of that to update it. And you always have a version that's working, and you can always do live demos without failing. So we're starting that with version 0.42. So super excited to do that. And we'll probably continue to do that with various other major packages.
So it looks like many people are still stuck. I think we are just trying to log on with a couple hundred people right away.
Yes.
So we can take it easy for now.
Yeah, it'll take some time. So let me just do some quick introductions of some of the features that we have. So we have something called OmniSearch. So if you are, I don't know if anyone has ever used this in this group, but if you search up WOMANIUM, for example, this allows you to see the WOMANIUM repository, search on Google, and then it will also search up on Qiskit or Stack Exchange as well. So, and we do have a nice feature with ChatGPT will be added in. So you can actually start to type in questions about quantum computing here, and you will be able to get results across 4 platforms and search for yourself and check. So another feature that we have is code snippets. So in these code snippets, you're able to essentially add various quantum computing snippets of your own, share them with others, and make private ones. And these snippets can essentially allow you to, again, if you've already impressed with how quickly you can code on quantum software packages on qBraid, these will make it a lot faster for you as well, because you can copy them and create new notebooks very quickly. And finally, we have quantum devices, which are all the devices that we have available. So these are, for example, AWS, and then you can check the status of whether it's offline or online as well. And you also have all of your quantum jobs that you're managing available on your right side as well. So this is just how the quantum computing platform for coding with notebooks is at the current state on qBraid. And we'd love to hear you guys' feedback. Wherever it is on the WOMANIUM Discord, just let me know, and love to learn more about what would help you guys be better coders and to learn more as well. All right. Okay. With that said, I'd like to point everyone's direction to either the qBraid lab demo if you already have it installed, or if you haven't, you can also use the launch on qBraid button and install it. Just added the notebook that is for this demo today. And if you don't, it's totally fine. If you'd rather not use launch on qBraid, your tutorials will also have this exact tutorial in the qBraid lab demos. So let me just repeat myself here and just make sure that everyone's following. You should see qBraid tutorials. We have tutorials from all of the major providers. Even Microsoft Q# is runnable on qBraid. And we have qBraid tutorials. These are our own tutorials, which are getting started on quantum, as well as our qBraid lab demo. So Just click on qBraid lab demo, and you should see yourself click on QCO_RL. So just let me know if you guys have gotten there. If you're unsure, or if maybe you don't see in the qBraid lab demo that you've cloned, maybe you cloned it like anytime before the last 3 hours. So then you can actually use this Git manager to discard your changes and then just pull the latest from the main branch as well. You can also use a terminal to do that if you're familiar with it, and just use Git from here as well. So Git is available. All right.
Several people have the error, we could not launch lab within the requested compute. You will have to put your compute on the spawn page.
Yeah, so if that's okay, that might be because you're a new user and we don't have your data saved on our Jupyter Hub system. Yeah, funny enough, it's like crazy how I know everything from start to finish. So yeah, so that is an API call that we're making to our Jupyter Hub, and that will not be working if you're a first-time user. So you'll have to just select whatever resource that you have available to in your account.
Will it be best to just listen to you and follow and then try yourself later?
Yeah, that might be good too. I think most of this demo, I think, is more followable, might be a little bit easier. And so with that said, to install that environment, you don't need a new access key because it's free. And do confirm with me if that's the case. If not, we can quickly fix that. But let's get started. All right, so I'd like to get started by just asking how many of you guys have, for example, ran the transpile function on IBM? I think a lot of people, a good amount of people have probably ran that, especially if you are maybe in qBronze and running it on a hardware or even on a simulator, you probably have ran the transpile function. And then quantum circuit optimization is something that occurs when you are using the transpile function. And so we're going to look under the hood today and use something called the path manager, which is used by the transpile function. Okay. First and foremost, if you have the WOMANIUM environment activated, I'd like you to make sure to select the kernel here. So click WOMANIUM and make sure that it's activated. And the first part of this demo will be a walkthrough, a live demo. So we'll do our imports. And so very quickly, I think most people would know what quantum circuit optimization is, but for those that are not familiar, right now, well, regardless of whether you're talking about fault tolerant or NIST quantum computing, quantum circuit optimization is super important because we want to get the most efficient circuit to run on a quantum computer. And most importantly, you want to reduce the gate and the depth, as well as there are some more hardware specific optimizations that you can do, such as the layout of the qubits, the coupling strategies as well for various hardware. Today, we're not going to be discussing any particular hardware, but what's really cool is the latter half of the demo with the reinforcement learning. You can actually tailor that to something that might be interesting with a hardware. Okay, so without further ado, looks like my imports have completed. So I'm going to just run the sample circuit here. And in this random circuit, you see that when you run the transpile function, we already see an optimization even at the second level, where the phase gate here, the Hermitian conjugate of the phase gate, as well as this unitary, are combined with the identity and moved over here as well. So that's probably what you may have experienced in much of your time, probably where you were running a circuit and you see this optimization. Maybe you've only ran the execute and then it's probably already doing the transpile underneath. But you can tell that the gate have reduced by 2 gates and the depth has stayed the same. So I don't know how many people have fooled around with the path manager, but the transpile function is actually calling the pass manager and then doing various processes to make sure that if you're targeting a specific hardware, the circuit is going to be as optimized as possible. So if you were to run, for example, on IBM's 16-qubit Guadalupe, you can get the preset pass managers from the transpiler, and you can tell that these are all the things that it's doing to make sure that the quantum circuit is going to run as efficiently as possible. Not all of these are going to be optimizations, such as check mapping is not necessarily an optimization that's going to reduce the circuit depth or the gate count. Sometimes you just need to check as well. And not all of these are going to be for moving the gates around if they are commuting and whatnot. So today we're going to discuss a few out of the many, many strategies that are available. All right, so with that said, I just want to stress that this notebook is a great starting point for if you're interested a little bit more about fooling around on your own about circuit optimization, because this field is very, very exciting and is full of amazing, smart people who are working on optimizing circuits. And the reason why is because we want to be able to run circuits for useful applications of quantum computing on NIST-based devices, and without error correction, one of the best go-tos is to make sure that your circuit is as small as possible, but is still going to return the intended expected value. So why is it hard? Well, one of the things is with a quick exercise, you can quickly actually arrive at suboptimal solutions. So imagine that you have this gate string here that's acting on 1 qubit. If you probably have learned about your identities in the qBronze course, and you know that the rotation gates Z, X, and Y, when applied all together, is the identity gate. So you may say, I see this gate here. Do you guys see my mouse? I think you guys do, right? Okay, yeah. So the ZXY gate here, I can reduce that and voila, maybe this is the fully optimized circuit, but that's actually not the case. What you have to also take a look is that you can inject an identity into this circuit, and I'm going to add it after the first Hadamard here. So you here see the Hadamard Y gate inserted here. Then you see that the rest of the circuit is still continuing. And because it's an identity, you can actually add it in without any effect on the overall results. And so then I can go back and say, well, I know that this identity is still here, and I actually see it here as well. So I can then remove those the 6 gates here and consider an identity. And up to a global phase, this will still be the same results. Then we get this. And lo and behold, now you have 2 Hadamards, which are once again an identity gate, and you can actually reach the globally optimal solution. So this is just a very quick example of how even small 1 qubit, 10 gate circuits can be non-trivial to optimize by hand, for example. So this is where you have to realize that this is not an easy process, for example, to figure out for if you don't know much about a specific hardware, or if you're not that familiar with all of your identity gates. And we can verify that this is the correct solution here. We have our circuits that we just mentioned. And once you run the transpilation, you realize that this is the equivalent circuit as Y times X. In fact, they transpiled it further to use a unitary that allows for rotations around X, Y, and Z. So that is pretty cool. Let me just check the time. So these large circuits, another issue is that the large circuits have a really large search space. So imagine if you had many, many more qubits and gates. Like, this is non-trivial, and we only talked about one single qubit gates, and we can have Toffoli gates as well as many multi-qubit gates, and it quickly becomes a very difficult task on to optimize the circuit. So with that said, we're going to quickly just run an example here, and you can do it on your own notebook. And I'd love to see how long it takes for you to run the random circuit, since this random circuit could actually give you different results. All right, so if you run this, you're going to see that we're going to be optimizing at various levels here. And some of it will take a long time, maybe not. Sometimes it might take not that long. But it all depends on the circuit that you get. Some circuits don't have a lot of gates because it's a random circuit. Sometimes the gates, in fact, may not be that optimizable. Sometimes it's very optimizable. So it's all dependent on how the gates are ordered, as well as, well, not necessarily just ordered, but how the random circuit is developed. But you can tell essentially that it's an exponential curve that you encounter when you are running your optimization. So it's very important to maybe find as efficient as possible for your optimization strategy, because if these are very doable, perhaps for a future NISQ-based quantum computer, and spending a lot of time to optimize would be a lot of pain. Some other notable challenges, which are very exciting, are the parameterized circuits. So optimizing parameterized circuits is another difficult but exciting field of research, as well as hardware constraints. So even if you've optimized your circuit for a 5-qubit device, it doesn't necessarily mean that it's going to run well on a 16-qubit device. The topology of the hardware might differ. All right, so with that said, what are some of the existing techniques? With each of the frameworks that you see here, including CERC, Qiskit, they all have their own optimization strategies for their own backends. And for Qiskit, these are all the ones that you have available. And today we'll talk about a few of them. All right, so the first one we'll talk about is the 1-qubit gate decomposition, where you are combining a bunch of single qubit gates that are next to each other into one gate, where they are applied as a unitary gate. And when you multiply this, you do get pi as the rotation here. And after this optimization for this gate here, you can tell that it has been correctly optimized using the optimizing 1-qubit gate decomposition pass. And to run these passes on any circuit, you want to first pass it to the pass manager, which essentially takes in an array of all the things that you want to do to the circuit, and then you get the result back and you can print it out. All right. So another thing is the cornerstone of quantum computing is commutations. And so you can actually check if a certain gate commutes with the adjacent gates, and then move them to essentially optimize any of the gates that will cancel. So for this example, you can tell that the gate here has the X gate 3 times because of the C0 gate. And because the C0 gate commutes with the X gate here, you can actually optimize these 2 gates and create an identity to remove them from the overall circuit as well. All right. So now you can go wild and start customizing your own transpiler. And in fact, you can even use the Unroller, which the Unroller will allow you to write it into the specific basis that you're interested in. So you could, as a suggestion, although not part of this demo, you could use the qBraid SDK, for example, to unroll to a specific basis and then run your device, run your circuit on IonQ, for example, run your Qiskit circuit on IonQ on Amazon Broadcast, for example. So we have this circuit, and we're going to once again combine the various strategies that we just talked about. So you have the commutation cancellation here, which cancels out the X gates, and our depth is decreased. Then we can unroll the gate into this current basis, which is the rotation gates and C0, which will give you this circuit here, very, very large. Sometimes as on optimization, unfortunately, causes a decomposition of the gates that were originally ran. And this is something that even on hardware, you may have to encounter. So sometimes like the amount of gates does increase. And then you can run the 1 qubit gate decomposition to once again reduce gate to get the depth of 25 gates, the depth of 25 for the circuit, and the gates of 32. All right, does anyone have any questions? So far, I think this is pretty standard. So now the question is, well, if you know how to fool around with the gates now, maybe you may be interested in learning what exactly is the best part or the best strategy to optimize. And there's various methods such as simulated annealing. And today we're going to talk about reinforcement learning as a possible method to correctly essentially make the best decision on which optimizer to use for our given a quantum circuit. So a quick overview of reinforcement learning. In reinforcement learning, and we're going to talk about the actor-critic model here, you have an actor here that is going to play around in this environment with various actions. So in this case, if you are Mario, you may have the actions to move up, down, left to right, and jump. And you will then use those in this environment and try and get a high reward. And if you're rewarded, then the circuit, the agent will say, aha, I did a good thing. And if it did a good thing, then it will continue to try and learn on how to best optimize the strategy here in this environment. So this agent and this actor-critic model is what we'll be using for our reinforcement learning. And so our agent here is a neural network, and our environment here is the actions, which will be the optimizations, and the circuit that we get back is our state, and our reward is how well we have optimized. So if we haven't optimized it very well, then we get a penalty. And then if we have optimized it well, then we get a reward and we get our circuit back. And then the agent updates its understanding of how to work in this environment. We are basing our work off of Google's Optimizing Quantum Circuits with Reinforcement Learning paper here. So if you're interested, you can click on that and follow along as well. So let me that into the chat as well. So with that said, we will be using Qiskit and we'll be using some of the optimizing that we have just learned about in this model. All right, so the model that we're using is called proximal policy optimization. And the reason why we do this at a very, very high level is because in reinforcement learning, some of the challenges that you have is, unlike supervised learning, where you have a data set for it to go off of, you're trying to make the neural network learn about a circuit or learn about an environment with the data that's provided by it. And the environment can always vary. So if you are in one level of Super Mario Brothers, like there may be fire, and then the other one may have water, and you have to kind of like navigate yourself through all these different kind of situations. And that's no different for random circuits. So some circuits are highly optimizable, some are already pretty efficient. And so you get various rewards out of it. And that is the proximal policy optimization is like perfect for that, where you have a varying distribution in terms of the data sets. Okay, so with that said, we're going to not do a full demo here, given that it does take a long, long time to run this, but we will really discuss the quantum environment that we have built. So if you want to follow along very quickly, you have to take this quantum circuit that you have generated from the random circuit, and I will show you what the environment looks like. It's available on the qBraid lab demo as well. And you want to convert it into a tensor so that the neural network can understand. And the method that was used in the paper is essentially to take the qubits and all the available gates that can be applied, and to assign essentially a value if the gate is applied on a certain qubit. So if you have an X gate applied on the third qubit, then you would just assign it a 1. And then they had another access for the moment. Moments are a notion in Circ, and we were using KISS gates. So I have instead replaced these with the index. So that would be the index would just be a value of 1. And then if there are parameters for the gate, so if you're applying a rotation around the y-axis, for example, then you would have some rotation parameters that are also added into this tensor. So that's how you input the circuit into the model, so for it to understand the results. And then we also have the reward. So when you apply an action, which is the optimization strategy, you also want to let the model know if it did well or not. So what you want to do here is this reward function says the value of the error probability of the circuit, is this at time t+1 better than the one at time t? So is your new circuit a better or more optimized than the prior circuit? And so just to give a high level overview, they give this kind of like probability of success, a metric here where M is the number of qubits, gamma is essentially the decoherence for idle qubits, as well as the total time it takes for the circuit to execute. And then it's multiplied by the multiplying sum of the set of gates and the time it takes for these gates to underperform. So doing some arithmetic here, you can get this function, and then what the paper does is essentially you can replace these with constants. So you can say that for each gate, it's roughly exponent to some constant beta time it takes to then simplify this function to, as well as the alpha would be the number of qubits and the decoherence time. So then this would be the reward function here, where you apply alpha, which is equal to 1, times the depth, plus beta, which is equal to 0.2, times the number of gates that are in the circuit. So if this goes down, then you get a smaller value here compared to this value, and the reward is positive. If this is larger, then this value is going to be positive, and therefore the reward is going to be negative. All right, so this is just a quick overview of that. And then the actions that we are taking, we've discussed optimizing 1-qubit gates, and we are also including unitary synthesis, commutative cancellations, CNOT cancellations, and inverse cancellations as well. And so this is kind of what the environment looks like. And I will hop over to the environment. And so the environment that I just mentioned is this playground for the neural network to learn in. And so you can tell that we have the minimum depth and the maximum depth of the gates are around 500, as well as the actions are set here. And you are creating a random circuit, then you are going to convert it to a tensor for the state, and then you would essentially train this model. Some notable functions that you need to think about is the step function. So every single time the neural network takes a step, it's trying to learn and it's going to apply an action. So we get back a float that we can then convert to an integer, which is the prediction, and the transformation is going to be added to the pass manager. And then we run the pass manager just like how we did in the first half of this demo. And then we compute our reward, which was what we have mentioned before, where you are going to take in the prior circuit and the optimized circuit, get the number of gates available and the depth for both of them, and subtract it to get the score. And then finally, you are going to then check if the score is going to be, well, you're going to get the reward back. And for our purposes, there is, for the sake of just getting a result, because this does take a long time, especially if you're going to add a transformation such as, or pass or optimization that is such as like unitary synthesis. If the reward, i.e. the difference between the performance of the optimized circuit and the prior circuit is 0 for more than essentially 5 times, then we say, okay, let's consider this episode, or let's consider this trial of optimizing this random circuit done, and then we will return the result of the collection of passes. And then we have every single time that it's said the environment is done, we will reset the circuit. We will create a random circuit, convert it to a tensor, and set that as an observation, and then pass it back into the model for it to relearn. All right. So I have 7 minutes. So I'm going to quickly show that this custom environment that we made, we can load it in. There is some various PyTorch reinforcement learning functions that we have to apply. So you take the base environment and we will normalize the observations, and then we initialize the environment with, then there's some parameters that we have set. Some of the opportunities that you can do to tweak this is actually reinforcement learning models are very hyperparameter sensitive, so you can actually set these to different results. We're going to roll the environment out, make sure that the results for the tensors are as expected. And then this is the neural network that we are applying. I think this is the one part that in the paper is not mentioned what the model actually looks like. I'm going to assume that it's much, much larger than this and much more complex, but they applied a convolutional neural network. So that is what we also do here. And then we essentially provide the output, which is the number of expectations, the actions, the set of actions that we have, the shape of it, and then we extract essentially the state and value with this extractor. So the state is what we mentioned here is the quantum circuit tensor, and then the reward is the value. So we have to extract these as well. Okay, so that is the actor running. We will build our model. Then we will do some further functions to set everything up. Then we also have our value model, which is the exact same model, but we needed to calculate the value. And then we run our policy as well. And we are going to use the advantage as well to kind of get a pre-idea of what the optimization strategy and how well it does. And then we run the result to get essentially this training reward was ran, I think, over 5 hours. And what you see here is that the value itself is not actually increasing. And what we know from this is that various random circuits are going to be optimized very well, and some of them are not going to be optimized very well as well. So that's why you see a lot of ups and downs. And even for the valuation, we kind of see similar results. But if you save the model and you run it, you evaluate it on a new circuit, and you take the prediction, you get a optimization according to the action. And once you pass that in, you are able to optimize a circuit as well. So with that said, this is definitely not a fully trained model. I think it would take 6 to 7 days according to the paper. But I hope that this kind of gives you a sense of a really good starting point on where you may want to learn a little bit more about maybe tailoring this reinforcement learning model for a specific hardware and training and getting some results. I think that's just a fun project that you can do, and you can actually extend this by perhaps like working on tensor networks or converting the mapping strategy for the circuits, tensor networks or DAG circuits, accounting for gate positions. So the tensor itself does not account for gate positions that well because we are essentially indexing. So if there's like a gate that occurs many, many times on a qubit, the index is only incremented by 1 and doesn't specify what the position is. You can improve the reward function as well, add your own custom passes to optimization, improve the step count. You can tweak the convolutional neural architecture, and the results are probably not that good as well because we're running random circuits, but you could create a reinforcement learning model that's very specific for QAOA or VQE, for example, and get some better results. All right. If you're interested in perhaps running this on a GPU, it might be significantly faster. We do have, we do have a type form for those who are interested. Please feel free to fill it out. All right. I am on time, just as I saw the message from Marlu, but okay. Anyone have any questions?
Awesome, Ricky. And many people are still trying to install everything, working on it.
Yeah, okay.
For Dan here as well. If you're available for a bit, we can try to get everything running, so everyone can try out by themselves afterwards.
Cool.
For Dan has been monitoring all questions and will help with that.
Sure. First of all, great lecture as usual. You have been like tremendous in explaining everything. This was a new approach for circuit optimization, and I hope most of the participants learned a lot from it. One common query which is being faced in the Discord is that the WOMANIUM environment is not being loaded, which I guess is because everyone is just trying it at the same time. But I believe in due time it will work out. Any other suggestions you would want to give on that note?
Yeah, I would have to go back to my VS Code and check what's going on there. But I'll let you guys know once it's fixed. So,
sure.
Yeah.
Some comments that people really enjoyed the lecture. It was a great lecture. Also a question from Erica, USA, is qBraid hiring?
Yes. We will probably be hiring very soon. We just finished a round of hiring, but one of the things that I'd like to mention here, if you are interested in working with qBraid, like one of the things that we love to see, and we actually hired someone from a hackathon because they were such a good coder. And in fact, CQ Tech is also an intern this summer because they took third at QHack. They use qBraid, and it's so awesome because they also contributed to Unitary Hack. So we love people who just get involved in qBraid. We have our own SDK, which has its own set of demos, which are super awesome. So please do let us know by actively contributing and being part of the quantum community. Like that is, I think, the best way to get started and catch our attention. So, yeah.
And someone asked, can this also be remote? And the one example you just gave is remote, right?
Yes. CQ Tech is remote, and they are doing a fantastic job. Yeah.
Perfect. So let me move on to the technical questions. There were a couple of them on the Discord chat. The first one is that what are the penalties for the algorithm you used? And the second one on a similar lines is that what data is being used to train the model?
Yeah, so that's a great question. So first and foremost, the penalty is essentially if your quantum circuit is, the depth is, for example, like let's just take this reward function at t+1. So as t+1, if your depth is much, much higher and your gate is much, much larger as well, your gate count and your depth count are much, much higher, then you're going to get a larger value here than this one, which would mean that this is a positive value, which multiplied by negative will result in a negative reward, and that's your penalty. So for our strategies, most of them will probably not do that because of the fact that they are all cancellations or decompositions that don't increase the gate depth or the circuit depth and the gate count. But that doesn't mean that you can't just swap these out for, say, the Unroller, for example, that we talked about, and that would increase it. And then you'd have to go back and just think a little bit hard about, well, what does my reward function then become? Then do I have to take into account that if it's in a different basis, do we want to consider that this is a new circuit, or do we want to consider it? How exactly do you consider a single qubit decomposition that increases into a bunch of gates for your reward? So you have to do a lot of thinking there, but it's very easy for you to just get started with various models, and you can make your own passes or add your own passes here and test it out for various hardware as well. You can actually adjust the basis too. So if you're interested, you can adjust the basis so then you know what perhaps like a specific hardware may have available too.
You briefly mentioned about the specific hardware, and on that note, there's a question in the chat that, is circuit optimization hardware dependent? And if yes, how do we proceed towards having an optimization dependent upon different architectures on the hardware?
Yeah, that's a very good question. So the demo today is only using virtual qubits where you don't have any actual mapping strategies because those don't really decrease the, well, it might, but essentially you could tailor this reinforcement learning model to work on a hardware. Either way, like you do have to know a lot about the hardware. So you may have to be an engineer or PhD that's working on it, and then you may know best about what the mapping should be, where to place swap gates, where to essentially, which qubits have the longest coherence times. Those are all the things that you have to take into consideration.
Another question is about the criteria for optimization. In this particular algorithm which you defined, only the circuit depth and the number of qubits are being considered. Are there any criteria other than those which should be kept in mind while optimizing the circuit?
Yeah, yes, this is a good starting point. I think it's like the best thing to say. So for here, like they also make the assumption that the beta is a constant here, as well as the number of qubits is a constant, as well as the essentially the qubit loss of information during idle time. So these are set as constants, but you can actually vary those parameters. It makes it much more complex, but there are many ways of actually adding in some considerations there as well. One of them is actually like moments. Like there's no notion of moments in the tensor that that is created here, but you could add that to actually distinguish where the positions of the qubits matter as well.
Another question is on the method of optimization. And the question is that, could you optimize small parts or some chunks of a complete circuit rather than optimizing the entire circuit at once?
Yeah, circuit cutting is, I think, like a really, I'm not that familiar with it, but I know that there are some people that are actively working on that as well. And maybe you could do that with this model as well. Essentially, like, I think what I really want to emphasize is that you can, it's very flexible to make like an environment that you can then train a model on and then see what the results are. So definitely give that a shot too.
Some of the participants are in a constructive discussion over here that this is a classical reinforcement learning, and I agree with that. But on that note, there's a question, can QML be used in a similar manner to optimize circuits?
I'm sure it can. I'm not entirely sure, to be honest. Maybe it would actually be a lot easier to then represent the circuit here as well. I would just be worried about like the, like QML, you're going to need a lot of qubits to do something very well. And I don't know if you'll get as much of a return as like using a bunch of GPUs right now, but maybe in the future.
Another question is that there seems to be many layers to the optimization stack. And how high up, like farthest from the hardware in the stack, do you need to know for which platform to optimize for?
By layers, this is not like the convolutional layers, but like just like layers as in like layers of understanding for the pass manager. Like that.
Yeah, I guess that's the question.
For the most part, I think on if you're using Qiskit or if you're using any of the frameworks, they have done a lot of the thinking for you. So you 90% of the time, you may not have to actually go into the transpilot. But I figured for a fun demo, like it's good to learn what's underneath and what's happening. So I think you're okay there, just coding on a regular making circuits and then just using the transpile function for like most of the time.
Mm-hmm. Another question is on the limit of the number of qubits. So the question is that, is there a limit on how many qubits this particular algorithm can optimize, or it could optimize any number of qubits?
That's a great question. So one of the advantages of using this kind of model is that you're not that constrained with the number of qubits. You could actually go up because think about it as like a classical tensors and just classical machine learning handle, for example, like images that are very, very large, and they have many like image channels. So you can consider this as an image. And we're only considering like 12 qubits here, but you could have a 256 by 256 bit image and just train on that very quickly. So my point I'm trying to say is that it's a very scalable method. I think that's one of the benefits that was mentioned in the paper.
A lot more questions are popping up gradually on Discord. And there's a question on something you mentioned right at the end of your discussion about having a GPU access from qBraid. Could you please elaborate?
Yeah, so on qBraid, we're going to be providing GPUs. So with qQuantum, wow, this is all right, let me just clarify. This is a sales pitch, so commercial time, but we do have various GPUs that'll be available with qQuantum. If you've ever installed NVIDIA, it's very difficult, and we have made it easy. So all you do is click a button, and then you have Penny Lane Lightning GPUs, as well as what was it again? Oh, qQuantum. So if you're interested in doing like a free trial with us, or essentially like a beta program that we're doing just to figure out what people like and what people don't, fill out the form.
Excellent. And the procedure for doing that?
Filling out the form.
Okay, great.
Let me. So here's the Discord. Everyone's still installing. Oh, okay. So it seems like it's working for some people. Oh no. Okay, we'll have to look into that. All right.
Great. So I guess I have fielded most of the questions, and the rest, I guess, are on the installation side. Once all the participants are able to install, they would be in a better position to try out all these notebooks. Yep. And just to reiterate the point, all these notebooks are available on the cloud and everyone can access them, right?
Yep. So not only are they available on qBraid Lab Demo here, but the qBraid Lab Demo folder is also available on your tutorials. So you should be able to access your tutorials as well. So go here, lots of clicking, but here, and then it's right there. So check out our other tutorials.
Wonderful. Yeah, so it was a great demo from you, Ricky. It's always great to have you here.
Yeah.
And here, the participants learned a lot. It was an amazing session. Once again, thank you for coming in. And yeah, thanks a lot.
Thank you.
Thanks so much, Ricky. This was really amazing. And it's great to have you on Discord all the time, helping out helping out otherwise. And thank you for being such a great partner of WOMANIUM.